Yes, sir.
Okay. So welcome to next lecture on boiler heat balance sheet. Today we are going to see numerical treatment. In previous lecture we saw this basic concept where heat is utilized at different parts. To just a quick recap, heat utilized to generate a steam. So we supplied a preheated water from economizer. So already water get preheated, that means its enthalpy is already rise. So enthalpy of water which is supplied to boiler is HFO. This enthalpy of water we are supplying to boiler. Then burning of fuel, that heat is supplied to this preheated water and steam get generated. Generated steam is always a wet steam because nobody can predict whether it is actually completely saturated steam or dry steam or superheated. So we presume that it is a wet steam. So wetness might be vary, 60% wet, 80% wet, 90% wet, 95% wet. So that is wetness of steam. So it may vary, but we presume that the steam generated in a boiler is a wet steam and it having an enthalpy H. So we change the enthalpy from HFO to H during this steam generation. Then this generated steam is supplied to superheater where we superheat and its enthalpy now rises to H super. So H SUP, that is suffix super. In economizer we supplied our regular water, that is normal room temperature water, having a enthalpy HFI, enthalpy of fluid at inlet to economizer, and after preheating it become HFO, enthalpy of fluid outlet to economizer. In the same manner we can say air preheater, it preheat combustion air. So supplied air is at temperature TAI, temperature of air at inlet, and outlet from air preheater is TAO, temperature of air at outlet. So these are the basic terminology, standard notations. Now, when we talk about a heat balance sheet, so it must be having some standard format. So the balance sheet having this kind of tabulated format, whatever be your calculations are there, but your final answer should be in this tabulation format, where at the top it is said that it is a heat balance sheet and it is divided in two parts. One is a heat supplied. So heat energy supplied, then its unit kilojoule per minute. If it is asked to find out the heat balance sheet on hour basis, so we will write kilojoule per hour. If it is asked to find out the heat balance sheet on second basis, so kilojoule per second, and kilojoule per second can be called as kilowatt. So many times it is not asked kilojoule per second, it is said that find the heat balance sheet on the basis of kilowatt. And the third column is percentage. How much is the percentage? So this is our first half where we give the detail of heat supplied. Second half of heat balance sheet is where heat is utilized. So heat energy utilized. In this also we have to write down the amount kilojoule per minute, as this heat balance sheet is assumed on minute basis. So kilojoule per minute, then its percentage. Now in details, so first part we write that heat supplied in fuel by burning of fuel obviously. So suppose that total amount of heat supplied is X, and the formula to calculate that total heat supplied is mass of fuel multiplied by calorific value. So MF multiplied by that fuel calorific value. So this gives one particular amount of heat generated. Now here, if we put mass of fuel in kg per minute. So our final unit will be kilojoule per minute. If mass of fuel is kept in kg per second, then our final unit will be kilojoule per second. Then we have to convert into kilojoule per minute. So always take a precaution to read unit. What is the given unit in your numerical and what is asked in heat balance sheet. So on the basis of that, we have to take a precaution to convert our unit. So heat supplied by burning of fuel, MF into CV, whatever be the amount, that X amount. So we will write that amount X in kilojoule per minute column. And then this is nothing but 100% heat. This is the total heat generated in a furnace. So at bottom, summarize, total heat supplied is amount X and it is 100%. Now out of this X amount, how much heat is utilized in different heads? So first head is heat utilized in steam generation, the main cause for which we are producing heat. So how much amount of heat is utilized in actual steam generation? It is never possible that total 100% heat is utilized for steam generation only. No, it is not possible. So how much amount of heat is generated for steam? So we know that suppose it is X1. So X1 amount of heat is generated. It is utilized in steam generation. So how it is going to calculate? So X1 is mass of steam generated multiplied by enthalpy change. Now enthalpy change. So remember, we supplied a preheated water, that is outlet water from economizer, and steam generated having wet steam having an enthalpy H. So change in enthalpy will be enthalpy of generated steam minus enthalpy of supplied water to boiler. If we don't use economizer, in that case, enthalpy of steam generated H minus enthalpy of room temperature water. But if we use economizer, so outlet of economizer, it is actually feeding to our boiler. So mass of steam generated. So mass of steam generated, it must be in kg per minute because we are drawing our heat balance sheet on minute basis. Then enthalpy difference. So it gives some amount of heat, that is X1. Now we have to find how much percentage of total heat is actually utilized for steam generation. So X1 amount is utilized for steam generation and we have total heat X. So take a ratio of that X1 upon X. So it gives how much percentage of heat actually used for steam generation. Next head, heat utilized in economizer to preheat that feed water. Now how to calculate that? Suppose that amount of heat is X2. Now one thing, it is very important that the amount of water feed to the boiler is always considered equal to the steam generated. Because whatever be the water level in the boiler, we have to maintain that water level inside the boiler only. Otherwise, your boiler get overheated. So it is considered that whatever be the conversion of water to steam, that much amount we have to top up from economizer preheated water. So many times it is said that it is not a mass of water supplied to economizer. It is equal to mass of steam generation. So actual water supplied is always equals to mass of steam generation. If in your numerical specifically it is mentioned that this much amount of water is a feed to boiler, then only we consider mass of water feed to boiler. Otherwise, mass of steam generation is equals to mass of water supplied to boiler. So in a formula itself, we consider mass of steam generation multiply by enthalpy change of water. Now enthalpy change in economizer. So we supplied water at HFI, this enthalpy, and after preheating, our water reached to HFO. So how much heat is utilized to preheat water. So mass of steam, that means total amount of water, multiply by change in enthalpy. Suppose this total calculation, we come to certain value, that is x2. So x2 is the total amount of 8 kilojoule per minute which is used in economizer. Now similarly we can find out the percentage, how much percentage of heat is utilized in economizer. So x2 upon x multiply by 100, so that much amount of percentage is used in economizer to preheat water. Now the third head, heat utilized in superheater to superheat steam. Now here also we assume that whatever be the steam generation, that total steam is directly supplied to superheater. So in a boiler, steam generation MS, that amount is supplied to superheater. So amount of steam superheated is always equals to amount of steam generation. Whatever be the amount of steam generation is always equals to amount of top of water, feed water. So here also the calculation we consider a mass of steam generation. So mass of steam generation multiplied by enthalpy change in superheater. Now we know that before superheater our steam having enthalpy H. After superheater our steam become superheated with enthalpy H super. So enthalpy change will be H super minus H and mass of steam generation. So this gives one particular amount of heat utilized, that is kilojoule per minute, and that is suppose x3. So we can find out how much percentage of heat, total heat, is actually utilized in superheating. Next, heat utilized in air preheater to preheat combustion air. Why it is required? Because if air having a moisture, just like a rainy season air, it is always humid. So your heat, one part is actually utilized to evaporate all the moisture content of the air. So total heat is not going to utilize for other purpose, it is utilized some part for preheating air itself. So to avoid that loss, what we did, we recover a waste heat to preheat air in air preheater. Now how it is calculated? So suppose x4 is the amount. Now we know that mass of air supplied is always based on mass of fuel supplied. So mass of fuel supplied, it is given in a kg per minute, kg per second, kg per hour. So with respect to time, that flow rate is given. But mass of air, it is given on the basis of per kg of fuel. So we have to calculate mass of total air supplied per unit time. So unit time may be in second, minute or hours. So we have to calculate total mass of air supplied per unit time. So mass of air multiplied by mass of fuel. So it gives mass of air supplied per unit time. Then multiply by Cp of air. Remember there are number of Cp, specific heat of moist air, that is steam, specific heat of exhaust gas, specific heat of air, specific heat of water. So there are many specific heat. We are talking about air preheater air. So specific heat of air multiplied by change in temperature in air. Where change in temperature? So in air preheater. So in air preheater we supplied air at TAI temperature. After preheating, its temperature become TAO. O stand for outlet, I stand for inlet. So it is a regular formula mCp delta T. So mass of air, total mass of air supplied per unit time. Here we are talking about per minute. So mass of air multiplied by mass of fuel, kg per minute. Cp of air multiplied by temperature change. Suppose that amount is x4. So calculate the percentage change. Now the fifth head is heat carried away by flue gases exhausted to atmosphere. After air preheater, We are not using any device to recover heat. So whatever be the heat remain in the exhaust gas after air preheater, that exhaust gases are exhausted in atmosphere. So that much amount of heat is wasted, which is a cause of thermal emission. But we have to calculate that. So how much amount? So it is calculated as, suppose X5 is the amount. So total mass of exhaust gas, just like a mass of air we calculated. So mass of exhaust gas multiplied by mass of fuel. Why? Because mass of exhaust gas also give in a terms of per kg of fuel. So per kg of fuel, this much amount of mass of exhaust gases are there. So we have to calculate total mass of exhaust gas. So mass of total exhaust gas is mg, mass of gas multiplied by mass of fuel. This will be in kg per minute multiplied by Cp of exhaust gas multiplied by temperature change. Now, what is the temperature change of exhaust gas entering to atmosphere? So exhaust gas entering to atmosphere is Tg4, exhaust gas temperature after air preheater, and atmospheric temperature is whatever be the air temperature, atmospheric air temperature, that is TAI. So this temperature air we already supplied to air preheater. So this is the atmospheric air temperature. So exhaust gas entering to atmosphere, that temperature minus atmospheric air temperature. So this is the temperature difference. This gives, suppose, X5 amount of heat kilojoule per minute. So percentage change X5 divided by X. Next head is heat carried away by moisture by combustion. So wherever there is a moisture content, might be it is possible that moisture itself in air, moisture itself in generated steam. So wherever there is a moisture, that moisture going to absorb some heat to get vaporized, and that heat is counted under this head 6. How it is going to calculate? So mass of moisture multiplied by mass of fuel. So mass of moisture per unit per kg of fuel is given. So total mass of moisture, because fuel itself having a moisture, suppose coal is there, and in rainy season suppose that coal get wet due to rain or wet air. So no doubt coal itself having some moisture, air having a moisture. So we have to consider all that. So mass of moisture multiplied by mass of fuel. This is total moisture multiplied by temperature, saturation temperature of steam minus temperature of air. Air, but which air? Outlet from air preheater, because we are not directly supply air to combustion chamber. We are supplying outlet of air preheater to combustion chamber, preheated air. So T saturation minus T outlet of air plus HFG. What is the HFG? HFG is the enthalpy of wet steam. Wet steam means there is a gas as well as moisture, moisture that is liquid, fluid. So H, enthalpy of fluid and gas mixture. If there is only fluid, then we said HF, enthalpy of fluid. If there is only gas, then we said Hg. But if there is a gas and fluid mixture, so it is denoted as HFG. Plus specific heat of superheated steam. Multiply temperature change. So temperature Tg4 minus T saturation. Suppose this amount is T X6. So percentage, how much percentage is there? Many times this 6 part is not considered. Why it is not considered? Suppose mass of moisture is not given. If mass of moisture is not given, then we cannot calculate this 6 part. So we are able to calculate only up to 5 parts. Then last part is unaccounted heat. So 6 part is then considered under unaccounted. If mass of moisture is not given, then no need to calculate this. We will consider this under unaccounted. But if there is a mass of moisture given, then we have to consider this 6 head. We have to calculate this part also. Now unaccounted means it is simply a difference. We know total amount of heat supplied is X minus whatever be the heat utilized head. So minus all these additions. So whatever be the difference is there, that is X7, and that called unaccounted. Why it is called unaccounted? Because some heat is lost by radiation, some heat is utilized to heat up the all boiler parts, boiler accessories, its enclosure, atmosphere. So all these heat is actually utilized there. That is a loss, and that is not, any formula is not there to calculate those. So we consider all those heat losses as a unaccounted heat. Now the most important, as this is a heat balance sheet, and whatever be the difference we consider in this seventh part. So addition of all these x1, x2, x3 up to x7, this must be equal to x, and the addition of this all these percentage, this must be equal to 100%. So it is advised, because when we write this balance sheet, so we use up to 2-digit numbers. Suppose 13.28. After that we don't use to write in a digit, even though we can round up it. And when we do the addition, so it most of the time it comes as not exact 100%, it comes as 99.98, 99.9. So don't show that there is some lacuna, there is some heat which is not considered. It is a balance sheet, so the last row it must be the perfectly balanced. So whatever be the your addition, don't do the addition, directly mention that total heat supplied X, it is 100%. So total heat utilized, again it is a sum of this, and whatever be the X amount is there, just write here. So total heat supplied is always equals to total heat utilized, and if it is equal, then this 100% must be equal to your heat utilized 100%. So this is your answer, final answer. If you calculate all these heads, no doubt you will calculate outside this box. But if you don't draw this heat balance sheet, then definitely there will be a separate weightage 3 to 4 marks to draw this heat balance sheet. This is your actual final answer. So whenever there is a numerical, you have to draw this heat balance sheet. Unless this heat balance sheet, you don't get out of marks. Now we will see one numerical, and that will be the end part of our today's lecture. So problem 1, following data relate to a trial on boiler using economizer, air preheater and superheater. So all three devices are there, and this is a schematic. We know how superheater, economizer and air preheater is there. Here for notation, T super, T steam, so steam generated temperature, then TFI, so fluid temperature inlet to economizer, TFO is the temperature of fluid outlet to economizer, TAI, TAO, temperature of exhaust gas outlet to boiler is TG1, after superheater it is TG2, after economizer TG3, and the temperature of exhaust gas which is actually entered to the atmosphere is TG4. Now the statement, condition of steam at exit of boiler is 20 bar and 0.96 dry. What do you mean by 0.96 dry? That means whatever be the steam generated, it is not 100% dry. Only 0.96% dry, that means 0.04% moisture is there. That means it is a wet steam. So when we said it is dry 100%, that is saturated steam, there is no moisture. Less than 100, that means there is a moisture. So it is 90.96 dry, that means 0.04 is a moisture. So it is a wet steam. This is actually a dryness fraction. So pressure is given 20 bar and dryness fraction is given, that is 0.96% dry. Next, temperature of steam at exit of superheater. What is the notation? Temperature of steam exit at superheater, we said T super. So T super is given 300. Next, steam evaporation rate kg of fuel is 12. Steam evaporation, so water get evaporate and steam is generated. So steam generation rate is given, that is the mass of steam generation, 12 kg per kg of fuel. Room temperature, so it is 25 degrees centigrade. So room temperature, so we assume that room temperature water supplied to economizer, so TFI is 25 degrees centigrade. We assume that room temperature air is supplied to air preheater, so TAI is also 25 degrees centigrade. Temperature of feed water exit to economizer, it might be written like that, temperature of feed water entering to boiler. So meaning is same. So outlet from economizer is 50 degrees centigrade. So TFO 50 degrees centigrade. Then temperature of air at exit of air preheater is 70. So TAO is 70 degrees centigrade. Temperature of flue gases at inlet to superheater, that is TG1. This temperature is going to enter to superheater. So TG1 is given 650 degrees centigrade. Temperature of flue gases at inlet to economizer, that is TG2. TG2 is 430 degrees centigrade. Temperature of flue gases at intake inlet to air preheater, so that is TG3. Then flue gases exhausted to atmosphere, that is TG4. This much temperature having exhaust gases which is enter into atmosphere. So TG4 is there. Then assume the air supplied. So mass of air 19 kg per kg of fuel. So mass of steam, mass of air, both are given per kg of fuel. And the fuel calorific value is given 45 kilojoule per kg Kelvin. Draw up heat balance sheet. This is our task. Also assume specific heat of flue gases and air. So Cp of exhaust gas and Cp of air is given. But if we observe that there is no rate of fuel supply, you have a steam generation rate per kg of fuel, you have a air supplied rate per kg of fuel, but they don't give a fuel supply rate. So in this case, we assume that it is a unit fuel supply rate. So unit fuel supply rate, that means 1 kg per minute. So this is our calculation part. So heat supplied by fuel burning. So mass of fuel burn multiplied by calorific value of fuel. Now here MF is not given. So what we did, we assume one, that is unit amount of fuel burn. That is also called per kg of fuel consumption. So unit fuel consumption basis heat balance sheet. So considering heat balance sheet on per kg of fuel consumption basis. So mass of fuel consumed is 1 kg. So given calorific value is 45. So total heat supplied is 45,000 kilojoule. Now here remember, we don't consider it is a mass of flow rate of fuel. It is only 1 kg. It is not 1 kg per minute or 1 kg per second or 1 kg per hour. So we are drawing this heat balance sheet on the basis of per kg of fuel only. So it is MF is 1 kg, this calorific value. So we don't get kilojoule per minute or kilojoule per second. We are directly getting the value of heat 45,000 kilojoule. So this is heat supply. Now second head, heat utilize. In heat utilize in steam generation. So mass of steam generated multiply by enthalpy change of steam. So mass of steam generated, enthalpy change is enthalpy of steam generated minus enthalpy of water supplied to boiler. So enthalpy of steam generated. Now steam is wet steam. That means steam having a gas as well as moisture. So how to calculate this enthalpy? So enthalpy of steam generated is the addition of enthalpy of fluid plus enthalpy of wet steam. But how much wet is that steam is wet? So it is according to dryness fraction X. So enthalpy of steam generated is addition of enthalpy of fluid plus product of dryness fraction and enthalpy of mixture of fluid and gas, HFG. We know what is the pressure, 20 bar. So using steam table, we will find out at 20 bar what is the amount of HF. It is given 908.6. What is the amount of HFG? It is 1888.6. So from steam table, we can use this value and calculate what is the enthalpy of steam. Most of the cases, all these values are given itself in your numerical. We don't require to find out, use that steam table. Nowadays, it is already given in a numerical statement. So H is known. From the steam table itself, with respect to this feed water temperature to boiler 50 degrees centigrade, we find out what is HF. So that is 209. So from steam table we get the value of these two. Put the values here. Mass of steam generated per kg of fuel is 12. So we come to know that 30148.8 is the heat utilized by in steam generation. Next, heat utilized in economizer. What is the amount of heat utilized in economizer? So mass of steam generated, enthalpy of feed water outlet from economizer minus enthalpy of feed water inlet to economizer. So MS HFO minus HFI. So from steam table itself, referring inlet temperature to economizer 25 degrees centigrade, HFI is 104.8, and referring outlet temperature of water from economizer, HFO is 209. Put the values. So we come to know 1254 is the amount of heat utilized in economizer. Next head is superheater. So mass of steam generated multiplied by enthalpy change of in superheater. So MS multiplied by S super minus H. So H super with respect to pressure 20 bar, T super is 300 degrees centigrade. We find out what is the value of H super. From steam table it is given. Then enthalpy of generated steam we already calculated in previous part. So put the values. We come to know 3639.6 is the heat utilized in superheater. Next head is heat utilized in air preheater. So mass of air supplied, specific heat of air, that is Cp, and temperature change of that air in air preheater. So we know Cp is given, PAO is given, PAI is given. So we are able to calculate total heat utilized in air preheater is 863.55. Now we observe that there is no data regarding your moisture, mass of moisture. So no need to calculate separate heat utilized in moisture. So next part is heat carried away by flue gases. So mass of flue gases, specific heat of flue gases, and temperature change. So mg cpg into temperature change, that is exhaust gas temperature entering to atmosphere minus atmospheric air temperature. Now how much is the mass of exhaust gas? Because mass of exhaust gas is not given. So it is considered that the mass of exhaust gas is always equals to the mass of fuel plus mass of air. Volume wise it might be different, but mass wise it remain equals to the addition of fuel plus air. So mass of fuel plus mass of air, we consider that mass of fuel is 1 kg and mass of air it is given that 19 kg. So total mass of exhaust gas is 20 kg. So we use mass of exhaust gas as 20 kg, remaining data we know. So put the values, calculate it, so it comes 3255 kilojoules. So it carried away by flue gases. Now unaccounted, because moisture content it is not given. So unaccounted heat loss. So difference, heat supplied minus all these head. So we come to know that it is 4939.05. So this is unaccounted. These all are the calculation part. Now we have to draw our final answer in heat balance sheet. So in heat balance sheet, never do the calculation part. It is a balance sheet representation. Now this is the standard format. Now here we have to put the values. After calculation, we come to know that total heat supplied 45000 kilojoule per kg of fuel, because they don't provide the fuel supply rate, and it is 100%. So in total last row 45,000 100%. Now heat utilized in steam 30148.8. Now its percentage, when we do the percentage, so it come to know that 66.99% is utilized in steam generation. Then economizer 2154, in percentage it is 4.79. Superheater 3639.6, in percentage 8.09% heat is utilized in superheater. Air preheater 1.92% amount of heat is utilized. Then exhaust gases entering to atmosphere, that is thermal pollution we can say. So it is 7.23% of total heat generation is exhausted into atmosphere, and unaccounted, so unaccounted is 10.98%. Now if we do the actual calculation, so no doubt there might be a possible that 45000 is not possible. So never do the addition, directly mention it 45, because it is heat balance sheet, both the head must be get balanced. So 45,000 and this 100%. So this is your final answer.